Welcome to the deep dive. Today, we're going to be tackling a real head scratcher,
Oh, yeah.
the cosmological constant.
Interesting.
You sent in some research from Living Reviews in Relativity,
Right.
specifically an article called The Cosmological Constant.
Right?
Buckle up because this one gets pretty wild.
All righty.
So, imagine the energy of empty space. Sounds strange, right?
Yeah.
That's basically what the cosmological constant represents,
Uh,
the energy density of the vacuum itself.
Hmm?
It's a concept that has huge implications for how our universe evolves.
I can imagine.
Here's the really crazy part.
Yeah.
Einstein first proposed this idea to try and create a model of a static universe,
Uh-huh.
one that wasn't expanding or contracting.
Okay.
But then Hubble's observations showed that the universe was expanding,
Right.
and Einstein famously called the cosmological constant his biggest blunder.
Yeah, I've heard that.
But hold on, there's a twist.
Okay.
Recent observations suggest that maybe, just maybe, Einstein wasn't entirely wrong.
Really?
To help us unpack all of this, we've got an expert in cosmology joining us today.
Well, I'm happy to be here.
So to start us off,
Yeah.
can you give us a quick rundown of why the cosmological constant is such a big deal in cosmology?
Well, the cosmological constant is mind-blowing because it acts like this weird anti-gravity force pushing everything apart. It throws a wrench into the works of our understanding of the universe's expansion.
Yeah.
It's like adding this extra energy that's constantly pushing outward, working against the pull of gravity from all the matter in the universe.
Okay. I'm already intrigued.
Good.
But before we get too deep into that, maybe we should back up a bit.
Sure.
Can you walk us through some of the basic concepts like Einstein's field equations and how they relate to the expansion of the universe?
Okay, so Einstein's field equations are essentially the foundation of general relativity.
Right.
They describe how matter and energy warp spacetimes, creating the phenomena we experience as gravity. Think of it like placing a bowling ball on a trampoline. It creates a dip. And that's kind of what matter does to spacetime.
Makes sense.
Now, when we apply these equations to the universe as a whole,
Okay.
assuming it's homogeneous and isotropic on large scale,
Meaning?
meaning it looks roughly the same in all directions,
Okay.
we get a set of equations called the Friedmann equations.
Oh, yeah, I remember reading about those. They're kind of like the rules of the road for how the universe expands, right?
Exactly.
Okay.
They tell us how the expansion rate of the universe changes over time based on factors like the density of matter and energy it contains.
Right.
These equations involve some key players.
Okay.
The Hubble parameter,
Yeah.
which measures how fast the universe is currently expanding,
Right.
and the density parameter, which compares the actual density of the universe to a critical density that determines its overall shape.
Right. And if I recall correctly, if the density is higher than this critical value, the universe is closed.
Yes.
And will eventually collapse.
Yeah.
If it's lower, it's open and will expand forever.
Yeah.
And if it's exactly equal, then the universe is flat, like a sheet of paper.
You got it.
Yeah.
And for a long time, cosmologists were trying to figure out which of these scenarios was true for our universe.
Right. Yeah.
Now, here's where the cosmological constant,
Okay.
represented by the Greek letter lambda,
Uh-huh.
comes into play.
Okay, so how does lambda shake things up?
Well, when you add lambda into the Friedmann equations, it's like adding a new ingredient to the cosmic recipe.
Okay.
It acts like an extra source of energy density, but with a crucial difference.
What's that?
It has negative pressure.
Negative pressure. What does that even mean in the context of the universe?
Okay, so imagine a balloon filled with regular air.
Okay.
The air pressure pushes outward on the balloon's walls, causing it to expand.
Right.
But negative pressure is like the opposite. It
Yeah.
pulls inward. So in the universe, this negative pressure associated with the cosmological constant actually counteracts the attractive force of gravity from ordinary matter.
So instead of slowing down the expansion of the universe,
Yeah.
like regular matter and energy do,
Yes.
the cosmological constant is actually pushing everything apart even faster.
Exactly. And this is where things start to get really interesting.
Yeah.
And where Einstein's blunder might not be a blunder after all. But to really understand why this is such a big deal,
Yeah.
we need to dive into one of the biggest mysteries in physics,
Okay.
the vacuum energy puzzle.
All right, let's hear it.
Okay.
What is this vacuum energy puzzle all about?
Well, you see, the cosmological constant is often interpreted as representing the energy density of the vacuum itself.
Okay.
That is empty space.
All right.
But the problem is that when physicists try to calculate this vacuum energy density based on what we know from quantum field theory,
Uh-huh.
which describes the behavior of particles and fields at the quantum level. We get an answer that's absurdly huge E,
What?
like 120 orders of magnitude larger than what we actually observe from the expansion of the universe.
120 orders of magnitude, that's practically an infinity. How can there be such a massive discrepancy between theory and observation?
That's the million-dollar question. Think of it like this. The energy we observe in the universe from all the stars and galaxies is like a single grain of sand on a beach.
Oh, okay.
But the energy we expect from the vacuum, based on our current understanding of physics,
Yeah.
is like the entire Sahara Desert. So where is all that extra energy hiding?
Okay, so we've got this enormous gap between what our theories predict for the energy of empty space and what we actually observe.
Right?
What are the possible sources of this missing energy?
Well, one is the zero-point energy of quantum fields.
Okay.
Essentially, even in a perfect vacuum with no particles, there are these quantum fields that fluctuate with energy. It's like a constant background hum of energy throughout space.
So even nothingness has energy. That's pretty mind-blowing.
Right. It's a consequence of quantum mechanics.
Okay.
Then there are scalar fields,
Yeah.
which are a type of field that can have a constant value throughout space.
Okay.
Their potential energy can contribute to the vacuum energy.
Right.
And finally, there's the possibility of a bare cosmological constant,
Okay.
a fundamental constant of nature that's just there, baked into the fabric of spacetime.
It sounds like there's a lot that could be contributing to the energy density of the vacuum.
Yeah.
But the big question is why the observed value is so incredibly small compared to what we expect.
Right.
It's almost like something is canceling out all these massive contributions, leaving just a tiny, tiny sliver behind.
Exactly. And that's why the cosmological constant problem is such a thorn in the side of physicists.
Yeah.
It's not enough to just explain why the vacuum energy isn't zero. We need to explain why it's this ridiculously specific, incredibly tiny value that we observe.
So where do we go from here? How do we even begin to tackle a problem this big?
Well, one way is to look for evidence that can either support or refute the idea of a cosmological constant.
Okay.
And that's where observations of distant supernovae come in.
Okay, supernovae, those massive exploding stars.
Right.
What do they have to do with the cosmological constant?
Well, a specific type of supernova called type Ia supernovae
Okay.
is incredibly useful for cosmologists.
Okay.
These supernovae are incredibly bright, and they all tend to have roughly the same intrinsic brightness, meaning how bright they actually are at their source.
Ah, so they're like cosmic light bulbs with a known wattage?
Precisely.
Cool.
And just like you can tell how far away a light bulb is based on how dim it appears,
Yeah,
we can use type Ia supernovae to measure distances in the universe.
makes sense. So how do these standard candles shed light on the cosmological constant?
Well, when astronomers started observing type Ia supernovae at very large distances, they found something surprising.
What?
They were dimmer than expected. And this dimming indicated that the universe was expanding faster than we previously thought.
It's like those supernovae were saying, hey, the universe is putting the pedal to the metal.
Exactly.
Uh-huh.
And to explain this accelerated expansion within the framework of general relativity,
Yeah.
we need something like a cosmological constant or perhaps another form of dark energy that behaves similarly.
So these distant supernovae, acting as our cosmic beacons, are hinting at the presence of this mysterious cosmological constant.
That's one way to put it.
But supernovae aren't the only piece of evidence, right?
Right.
Yeah.
We also have the cosmic microwave background, CMB radiation,
Oh, yeah.
which is like a baby picture of the universe taken just a few 100,000 years after the Big Bang.
The CMB, I've always been fascinated by that.
Yeah, it's pretty cool.
It's like a snapshot of the universe's earliest moments, frozen in time. What does it tell us about the cosmological constant?
The CMB carries a wealth of information about the early universe,
Okay.
including its composition and geometry.
Great.
One of the most important features of the CMB
Yeah.
is its temperature fluctuations,
Hmm.
tiny variations in temperature across the sky.
So it's not perfectly uniform.
Yeah,
There are these subtle hot and cold spots.
exactly.
Wow.
These fluctuations are the seeds of the large-scale structure we see in the universe today,
Okay.
like galaxies and clusters of galaxies. And the patterns of these fluctuations depend on the geometry of the universe.
I see. So the shape of the universe affects how these temperature variations appear to us.
Right. Measurements from satellites like COBE and WMAP have shown that the universe is very nearly flat.
Okay.
And when combined with measurements of the matter density,
Hmm.
strongly suggests the presence of a cosmological constant to account for the missing energy density.
It's like we're piecing together a giant cosmic puzzle with the supernovae, the CMB, and the matter density all providing clues.
That's a great way to put it. Each piece of evidence adds to the bigger picture, and it's pointing toward a universe where the cosmological constant plays a significant role.
This is incredible stuff. We've covered a lot of ground already, but there's still so much to discuss.
Absolutely. We've barely scratched the surface of the cosmological constant and its implications.
Right.
Next, we'll delve into the attempts to explain this mysterious dark energy and how it might shape the future of the universe.
Okay.
But first, let's take a moment to let all this amazing information sink in.
Yeah, that's a good idea.
Don't go anywhere. We'll be right back with more of the Deep Dive.
Sounds good.
Welcome back to the Deep Dive. We've established that the cosmological constant is back in the spotlight, and it's causing quite a stir in the world of cosmology. Now let's dive into the heart of the mystery. What could this dark energy actually be?
Yeah, that's the big question, isn't it? We've talked about the evidence pointing toward a non-zero cosmological constant, but what are the leading explanations for what this mysterious force might be?
Well, one of the simplest explanations is that dark energy is indeed a cosmological constant, a fundamental property of space-time itself, just like the speed of light or the gravitational constant. It's a fixed value that doesn't change over time or space.
So it's like a built-in feature of the universe, a cosmic background energy that's always there.
Exactly. And the good news is that this simple explanation fits the current observational data quite well. But of course, there's a catch.
There's always a catch, isn't there? What's the downside of this cosmological constant explanation?
The main issue is that it doesn't really explain why the cosmological constant has the value it does. Remember that huge discrepancy we talked about earlier? The 120 orders of magnitude difference between theoretical predictions and observations?
Oh yeah, the whole Sahara Desert versus grain of sand analogy. That's a pretty big elephant in the room.
It certainly is.
Yeah.
And it makes many physicists wonder if there's a deeper explanation, something more dynamic and perhaps even more fascinating than a simple constant value.
Intriguing. So, what are some of the alternative explanations out there? What else could dark energy be besides a cosmological constant?
One of the most popular contenders is something called quintessence.
Quintessence, that sounds almost mystical. What is it exactly?
Quintessence is the idea that dark energy is not a constant, but rather a dynamic field, a form of energy that can change over time and space. Imagine a field that permeates the entire universe, and its energy density can fluctuate a bit like the surface of a rippling pond.
So instead of a fixed cosmological constant, we've got this quintessence field that's sort of sloshing around, influencing the expansion of the universe in a more dynamic way.
That's a great analogy. And the interesting thing about quintessence is that it could potentially address some of the fine-tuning problems associated with the cosmological constant. For instance, maybe the quintessence field is still evolving, and it just happens to have a value comparable to the matter density right now.
So it's a cosmic coincidence, a brief moment in the universe's history where the two densities are roughly equal. But this coincidence could change over time as the quintessence field evolves.
Exactly. And there are even more intriguing ideas within the realm of quintessence, like the concept of tracker fields.
Tracker fields. Now I'm really curious. What are those?
Tracker fields are a special type of quintessence field that have a remarkable property. Their energy density naturally tracks the dominant form of energy in the universe.
Wait, so they adapt to whatever's in charge. So in the early universe, when radiation was dominant, the tracker field would have mimicked the behavior of radiation. And then when matter became dominant, it seamlessly switched to tracking the matter density.
Precisely. It's like these tracker fields are cosmic chameleons, blending in with the dominant energy form and subtly influencing the universe's expansion. And eventually, as the universe continues to expand and matter thins out, the tracker field could take over, becoming the dominant form of energy and driving the accelerated expansion we observe.
That's an incredibly elegant idea. It could explain why the dark energy density is comparable to the matter density right now without requiring any extreme fine-tuning. But if these tracker fields are so adaptable, shouldn't we be able to see their effects throughout the history of the universe?
You would think so, wouldn't you? And that's one of the challenges with quintessence and tracker field models. We need to figure out exactly how they would have influenced the universe's evolution over billions of years and look for observational signatures of these effects.
So it's a promising avenue of research, but there's still a lot of work to be done to test these ideas.
Absolutely. The quest to understand dark energy is still in its early stages. And besides quintessence, there are even more radical and mind-boggling ideas out there.
Radical and mind-boggling, now you're speaking my language. Tell me more about these other contenders for the role of dark energy.
Well, some physicists are exploring modifications to Einstein's general theory of relativity itself. Maybe, just maybe, gravity doesn't behave exactly as we think it does on the largest scales of the universe.
So Einstein's masterpiece needs a little tweak to account for dark energy. That's a bold proposition.
It is. But remember, even the most successful theories can be refined and improved as we gain new knowledge. There are a number of modified gravity theories out there, each with its own set of predictions and challenges.
It sounds like we're venturing into uncharted territory here. What are some of the key ideas behind these modified gravity theories?
One common theme is that the strength of gravity might change depending on the scale you're looking at. So gravity might behave as we expect on the scales of planets and stars, but on the vast distances between galaxies, it might weaken, allowing the universe to accelerate its expansion.
So it's like gravity has a split personality acting one way in our local neighborhood and another way on the cosmic highway.
That's one way to think about it. But modified gravity is just one of the exotic possibilities on the table.
Okay, bring on the exotic. What else is there?
Another intriguing idea is that dark energy might not be a fundamental force or field at all, but rather an emergent phenomenon arising from the collective behavior of a vast number of microscopic objects. Imagine a cosmic sea filled with tiny black holes, cosmic strings, or other hypothetical entities. Their collective interactions could create a repulsive effect that mimics the behavior of dark energy.
So dark energy could be like the pressure in a gas arising from the random motions of countless individual molecules. It's fascinating to think that something so grand and mysterious could emerge from the collective behavior of tiny unseen entities.
Exactly. It's a very different perspective, and it's still in the early stages of development, but it's certainly worth exploring.
It sounds like we've got a whole buffet of possibilities here. Cosmological, constant quintessence, modified gravity, emergent phenomena. How do we even begin to narrow down the options and figure out which explanation is most likely?
That's the exciting challenge for cosmologists. We need more data, more observations to help us distinguish between these different theories.
What kind of observations would help us solve this cosmic mystery?
New telescopes are being built that will be able to map the distribution of galaxies and dark matter in the universe with unprecedented precision. By studying how the large-scale structure of the universe has evolved over time, we can gain valuable insights into the nature of dark energy.
So it's like we're creating a 3D map of the universe's history to track the fingerprints of dark energy.
Exactly. And in the meantime, we need to continue developing new theoretical frameworks and making predictions that can be tested against observations.
It sounds like the quest to understand dark energy is a collaborative effort between observers and theorists working together to unravel one of the biggest mysteries in modern science.
Precisely. And who knows, maybe the key to solving this puzzle lies in some completely unexpected direction. Perhaps a revolutionary new theory will emerge, or a groundbreaking observation will change our understanding of the universe in profound ways.
This whole discussion has been a mind-bending journey through the frontiers of cosmology. But there's one more idea that I'm really curious about, one that often sparks debate and controversy: the anthropic principle.
Ah, yes, the anthropic principle. A fascinating and sometimes frustrating concept that suggests our very existence might be intertwined with the nature of the universe itself. It's a deep rabbit hole, but worth exploring.
I'm ready to jump down the rabbit hole. What is the anthropic principle all about, and how does it relate to the cosmological constant?
The basic idea is that the universe we observe must be compatible with the existence of observers like ourselves. Otherwise, we wouldn't be here to observe it in the first place.
Okay, that makes sense on a basic level. If the universe were fundamentally hostile to life, we wouldn't be around to ponder its mysteries. But how does this principle apply to the cosmological constant and dark energy?
Well, consider this. If the cosmological constant were much larger than it is, the universe would have expanded too quickly for galaxies and stars to form. The universe would be a vast, empty expanse, devoid of the complex structures needed for life as we know it.
So our existence places a constraint on the possible values of the cosmological constant. Only universes with a cosmological constant within a certain range can support life as we know it.
Exactly. It's like a cosmic selection effect. We find ourselves in a universe that's hospitable to life, because if it weren't, we wouldn't be here to have this conversation.
That's a pretty profound thought. But some physicists find the anthropic principle a bit unsatisfying, like it's giving up on finding a more fundamental explanation. What are your thoughts on this?
The anthropic principle is certainly a controversial topic. Some see it as a powerful tool for understanding why the universe is the way it is, while others view it as a philosophical cop-out. Personally, I find it to be a valuable perspective, a reminder that we are part of the universe and our existence is intimately connected to its properties. But it's important to remember that the anthropic principle doesn't replace the need for a deeper understanding of the underlying physics. We still need to explore those other explanations for dark energy, like quintessence and modified gravity, and see where they lead us.
So the anthropic principle is more like a guiding principle, a way of framing our thinking about the universe rather than a complete explanation in itself.
Exactly. It helps us to appreciate the delicate balance of conditions that make our existence possible. But it doesn't absolve us from the responsibility of seeking a more complete understanding of the laws of nature.
Welcome back to the deep dive. We've journeyed through this strange world of the cosmological constant,
Yeah.
from Einstein's regrets
Right.
to the mind-boggling energy of empty space.
Absolutely.
Now let's face the ultimate question.
Yeah.
What does the future hold for a universe where dark energy seems to be in the driver's seat?
Oh, that's the big question that keeps cosmologists up at night.
Hmm.
The fate of the universe is intimately tied to the nature of dark energy. And right now, the leading contender is still that cosmological constant, that unchanging energy density woven into the fabric of space-time.
Okay, so let's assume for a moment that the cosmological constant is the correct explanation for dark energy.
Okay.
What would that mean for the universe's long-term evolution?
Well, if the cosmological constant is truly calling the shots, then the universe is on a one-way track to an ever-expanding, ever-accelerating future.
Okay.
As the universe expands, the matter within it gets more spread out.
Right.
But the cosmological constant, being a property of space itself,
Yeah.
doesn't dilute.
Mm.
It's like a cosmic yeast that keeps rising no matter how much dough you spread out.
So the more the universe expands, the more dominant the cosmological constant becomes.
Right.
Like a self-reinforcing cycle of expansion.
Exactly. As the cosmological constant's influence grows, the expansion of the universe accelerates,
Okay.
pushing galaxies farther and farther apart.
Yeah.
Eventually, the expansion becomes so rapid that it overwhelms the gravitational pull between those distant galaxies.
That sounds a bit lonely.
It is.
A universe where galaxies are scattered across the vast cosmic ocean like ships that can't communicate with each other?
Yeah, it's a rather bleak picture, isn't it?
Yeah.
A universe where the night sky grows increasingly empty
Hmm.
as
Oh.
distant galaxies recede beyond the reach of even the most powerful telescopes.
Right.
But there's another intriguing possibility, a twist in the tale,
Okay.
that might offer a glimmer of hope.
Tell me more. I could use some cosmic optimism right now.
What if the cosmological constant
Yeah.
isn't actually a constant?
Mm.
What if it's just a placeholder for something more complex and dynamic?
Yeah.
Something that might change over time.
We've talked about those alternative explanations for dark energy, like quintessence and modified gravity.
Right.
Are you saying those could lead to a different fate for the universe?
Exactly. Remember those tracker fields we discussed?
Yes.
Those clever cosmic chameleons that adapt to the dominant form of energy in the universe.
Yeah, they track the energy density of whatever's in charge.
Right.
First radiation, then matter, and eventually perhaps something else entirely.
Precisely. Now imagine a scenario where the tracker field eventually catches up to the cosmological constant, mimicking its behavior for a while.
Okay.
But then something shifts,
Yeah.
and the tracker field evolves,
Okay.
changing the dynamics of the universe.
So the universe could go through a phase of accelerated expansion driven by the tracker field mimicking the cosmological constant.
Yeah.
But then something changes and the expansion slows down, or maybe even reverses.
It's possible.
Cosmic U-turn.
It's a possibility, however unlikely it might seem.
Right.
Or perhaps modified gravity comes into play,
Okay.
subtly altering the strength of gravity on cosmic scales, leading to a different expansion history altogether.
So the future of the universe is still an open question.
It is.
With multiple possibilities on the table.
Absolutely. We're still in the early chapters of this cosmic story.
Yeah.
There's so much we don't know about dark energy and its role in the universe's grand narrative.
Yeah.
But with each new observation, each theoretical breakthrough,
Yeah.
we inch closer to understanding the ultimate fate of our cosmic home.
It's both exciting and humbling to realize that we live in a universe where such fundamental questions are still unanswered.
It is indeed.
And
And
so-
perhaps that's the most beautiful aspect of cosmology. It's a constant reminder that there's always more to learn, more to explore, and more to wonder about.
I'm certainly filled with wonder after this deep dive into the cosmological constant.
Good.
It's amazing to think that something we can't even see or touch, this mysterious energy of empty space, could hold the key to the universe's destiny.
Yeah, it really is.
Well, you've certainly given me a lot to contemplate. From Einstein's regrets to the mind-boggling energy of the vacuum and the uncertain fate of the universe, this deep dive has been an incredible journey.
It's been a pleasure sharing this journey with you.
And to all you fellow knowledge seekers out there, remember, the quest for understanding is never truly over. Keep asking questions, keep exploring, and keep looking up at the stars with wonder.
Because within those distant points of light, within the vast expanse of the cosmos, lie the answers to some of the most profound questions we can ask.
Thanks for joining us on the deep dive, and until next time, keep those brains buzzing.